Hello, everyone. I'm Luisa Lucie-Smith, and I'm a research fellow at the Max Planck Institute for Astrophysics. And today I'll be telling you a bit about how we can use deep learning to try and understand a bit more to gain some physical insights into cosmological structure formation. And this is work I've been doing with Hiranya Paris and Andrew Ponson at UCL, Brian Nord at Fermilab, and Jayan Tiaglingam at the STFC. So let me just start with a brief outline of my talk. So I will start with explaining how we can train a deep learning algorithm to learn the mapping between the initial conditions and the final cosmic structures within n-body simulations. I will then present a technique to physically interpret this learned mapping, and in particular, what physical information is the VAE model using to make its predictions about the final cosmic structures. And then I will conclude showing you that we can use this technique to gain new knowledge about the underlying physics driving cosmological structure formation. Despite not knowing most of the ingredients of our standard model in cosmology, actually the lambda CDM model is very successful at describing the evolution of matter in the universe. So the idea is that at early times, the universe is just made of tiny, small perturbations in the density of matter. And through cosmic time, these grow more and more to form the complicated large-scale structure that we observe today. So this is made of these large overdense regions, which are dark matter halos, that are interconnected by filaments and surrounded by these large empty regions, which we call cosmic voids. In this talk, I will focus on dark matter halos. So dark matter halos are the fundamental blocks of cosmic large-scale structure where galaxies form and reside. And so understanding how they form and how they evolve is really important for galaxy formation and to test our cosmological models. So the idea is that they start from, again, early times where you have small perturbations where the density of matter can be very well described by a Gaussian random field. And as the universe evolves, these tiny regions that were slightly overdense in the initial density of matter grow more and more to form this very large, nonlinear dark matter halos. And so the most accurate method that we currently have to model this nonlinear evolution and the formation of dark matter halos is through n-body simulations. So with n-body simulations, you start from your initial conditions and you evolve the field through gravity to then form your final logical structure. So the problem is that numerical simulations are hard to physically interpret in the sense that it's hard to know what exactly about the initial perturbations led to a particular mass, a spin, a shape, or the structure of the dark matter halos. And so typically numerical simulations are accompanied by analytic models that typically make some quite simplistic assumptions about how dark matter halos form. And so due to this sort of the limited complexity of these models, we can really only gain a qualitative understanding of how dark matter halos form. So what we wanted to do is to see, well, actually, can we use machine learning to gain some insights into how dark matter halos form? So the approach is to train a machine learning algorithm to learn the mapping between the initial conditions and the final dark matter halos in your n-body simulations. And I want to stress here that this approach is used for many, many different science goals, but here really it's not so much to have a quick mapping from initial conditions to dark matter halos or a quick mapping between input and output that can substitute in some way the n-body simulation. Our aim here is really to try and gain some further insights into how dark matter halos form. And so using the machine learning model to try and understand more about dark matter halo collapse. Okay, so how do we actually turn the problem of halo formation to a deep learning model? Well, we start off with the initial conditions. So the initial conditions are a realization of the density field that comes from the known power spectrum of that field that we know very well from our cosmological model. So we can create different realizations of the initial Gaussian random field. And then through the n-body simulations, as I said, you typically take these initial conditions box and you just through the laws of gravity evolve it up to today, redshift 0, where you can then extract the dark matter halos and look at their properties. So in this work, we focus on halo mass, just because it's the primary characteristic of halos, but this work could be extended to any other halo property of interest. So what we do is that we construct a 3D convolutional neural network that takes as an input the initial conditions density field in the 3D box. So this is the same input that goes in through the n-body simulation and then produces the resulting dark matter halos. So we want to use that same input, the initial conditions in a 3D box, and pass it through a series of convolutional layers in 3D, because your input subbox is in 3D, and predict the final mass of the halos at redshift 0. Now, of course, for a single simulation, so for a single initial condition box, you have many, many different halos. So how do we create a unique initial conditions to halo mass mapping? Well, we do this for every particle in the simulation. So from the n-body simulation, you can go to your redshift 0 snapshot. You can look at which particles belong to every single halo. And for each of those particles, you can trace back to its position in the initial conditions. So then for our CNN model, the inputs are the initial density field in a sub-box of the whole simulation box, centered on the particle's position. And then the output is the mass of the halo to which that particle belongs. So for every particle in the simulation, you have a mapping between the surrounding initial density field of that particle in the initial conditions, so a box centered on that particle's position, and the output is the mass of the halo to which that particle belongs at redshift 0. So then you can do this for many, many particles, many examples of different particles across many different simulations. And the model then learns to identify which aspects of the initial density field surrounding each dark matter particle is relevant, which aspects impact the final mass of the halo where that particle will end up in. Okay, so why do we want to use convolutional neural networks? Well, the fundamental reason is that convolutional neural networks don't require featureization. So this means that you can provide as input to the CNN the raw data, which in our case is the initial conditions density field sampled in the 3D box. So you don't need to sort of pre-process in the data to find what features might be relevant like you do for other more standard machine learning algorithms. With CNN, you can just directly provide it the raw data, so the initial conditions density field, like you would do for the n-body simulation. And then the CNN actually extracts the relevant features itself through the convolutional layers of the network. So it's the CNN itself that identifies which initial conditions features are relevant to predict the final halo mass. And this is exactly what we wanted, because we wanted to gain more physical insights into the properties of the initial perturbations that lead to final halo masses. Now, the disadvantages are that deep learning algorithms are so-called black boxes. So they're very hard to understand internally how they reach certain predictions. So how can we actually extract physical knowledge from a deep learning algorithm? Now, let's first look at what the CNN model actually looks like. So for people that are experts in machine learning, this is actually quite a simple model. So we have 6 convolutional layers with a nonlinear activation function after every convolutional layer, and then a max pooling layer, which essentially reduces the dimensionality of your outputs throughout the network. So this is the feature extraction part, is where the inputs get convolved with a number of kernels, these kernels are just 3D kernels, 3D matrices that that perform convolutions with the inputs to detect specific features. So each kernel is there to detect a specific feature. And as you go through more and more layers, you extract these features in a hierarchical fashion. So this means that in the first layers, you tend to extract low-level, small-scale features, and then in subsequent layers, you extract more higher-level, larger-scale features. So once you've done this feature extraction part, these features then get assembled into two fully connected layers that basically allow you to go from the features to the final halo mass prediction. Okay, so once you've constructed the network that you're going to use, the next step is actually to train this model. So training a CNN model essentially means minimizing a loss function that depends on a set of parameters, the parameters of your network, and you want to find the set of parameters that minimize your loss function. So the loss function that we have for this problem is made of two terms. One is the so-called predictive term. So this term tells you essentially how close are your predictions to the ground truth values. And this is essentially comes out of the likelihood. So I'm happy to talk about this more in the discussion. But we assume a Cauchy likelihood and write down this predicted term essentially as the negative log of a Cauchy likelihood. The second term is instead a regularization term. So this term acts as a term that basically helps you regularize the network, helps you reduce overfitting, and moreover, it compresses your network to try to use the minimum number of components or of neurons in the network. So it does this by promoting sparsity. And this is just an outcome of the specific choices of priors that we use for the weights. So all you have to remember is really that this loss function is made of a likelihood term that we choose for it to be a Cauchy distribution, and a regularization term that is just setting priors over your weights. And then the final set of parameters are those that minimize this loss function. Okay, so once you've trained your network, you can actually test it on a set of dark matter particles that come from independent simulations that the network hasn't seen before during training. So as I said, you have your trained CNN, you have your inputs, which is the sub box surrounding the dark matter particle in the initial conditions, and your output is a prediction for the mass of the halo to which that particle will belong at redshift 0. And then you can compare that to the true halo mass for that particle. So what this plot here is showing you is the predicted halo masses as a function of the ground truth mass. So I'm showing you as distributions within bins of true halo mass. So you can see that these distributions look like they have quite a large variance and quite a large skew, although one would say that the maximum posterior is more or less in the right location, which is this y = x line here. So the question is, okay, well, these predictions look like they have quite a large scatter. What information has the algorithm learned that returns this scatter, that returns this set of predictions? So this is where a technique to interpret the deep learning model comes into the picture. So this is quite a simple and yet effective technique where essentially you just remove part of the information carried by the inputs and retrain the model. And then by doing so, you can measure the resulting change in the model's performance compared to your original model. So basically you remove part of the information, the inputs, retrain, and see how your predictions were affected by removing this part of the information. So what we wanted to test here is what is the role of anisotropic information in the initial density field? How much does the anisotropic information impact the final halo mass compared to just isotropized density. So what we do is that we take our input subbox with the raw initial density field, and we remove anisotropic information from these inputs. So we do this just by taking the average of the density over the shells. So you can see that in this case, the inputs just contain information about the average, the spherical average of the density field surrounding the dark matter particle. So then we end up with two models. One where we're giving as input the full information, so the raw density model, the raw density training set, and the other where we only give it information about spherical averages over the density field. And so we call this average density model. So then the next step is to compare the predictions between these two models. And what we find is actually that the predictions look very similar. These three panels here show the residuals, so the predicted value divided minus the truth for three mass bins of halos. And so what you can see here is the histogram for the average density model, which is the one trained only on spherical averages over the density, and the histogram for the raw density model, trained on all the information in the density, so both anisotropic and the isotropic part. And what we find is that these predictions are consistent, which means that the features that the algorithm is learning actually are equivalent to spherical averages over the density field. And this basically allows us to conclude that anisotropic information plays no role in establishing final halo masses, and that the only information that matters to establish final halo masses is saturated in spherical averages over the density field. So the next step that we're taking along this direction of trying to extract physical knowledge from deep learning models is what we call the supervised variational encoder. So in the work that I just told you about, we needed to have a hypothesis to test. So we wanted to test what is the role of anisotropic information in establishing final halo masses. So what we want to do next is to have a model constructs an architecture where you don't have to make a hypothesis like that, but where you can actually directly try to understand what these what the features are that the model is learning. So to do this, we basically use convolutional layers to compress the information in the initial density field into a one-dimensional vector, into a low-dimensional space that we call the latent representation. And then used these latent variables, these latent representation, to make predictions about, say, for example, halo mass. And so what we hope is that these latent variables will encode the most relevant aspects of the initial density field that are relevant to predict final halo mass, or it could be any other property. So in this way, by interpreting what is the information contained in these latent variables, we can actually make some statements about the physics that is relevant to a particular halo property, or in this case, halo mass. Okay, so let me just end by saying that I hope that I've convinced you that interpretable deep learning frameworks are really a powerful tool to try to gain insights into cosmological structure formation. And this work in particular, it turned out to reveal some unexpected results into the role of anisotropic information in the initial density field in establishing final halo masses. We are now employing a supervised variational encoder where we try to compress the information into a low-dimensional space, which then can be more easily interpreted into physical parameters with respect to a certain halo property. And in future work, I'm planning to apply these sort of techniques to other halo properties, such as the profiles of halos, and also other cosmic structures, such as voids. So thank you very much for listening, and hope to discuss further in the discussion session.